Welcome to the presentation of the paper on an upper bound and linear space queries on the LZ parsing. My name is Dominik Kempa and this is joint work with Parna Saha. The field of compressed indexing aims to design efficient data structures and their construction algorithms to store any highly repetitive text T in space close to its compressed size, simultaneously supporting various queries on the original text T. Examples of supported queries are the longest common extension or LCE queries that compute the length of the longest common prefix of any two suffixes, pattern search queries, or even full suffix array and suffix tree functionality. One of the natural questions in this field is how to measure if a text is highly compressible. A number of possible answers have been suggested over the years. The list of such measures includes the well-established measures such as empirical entropy, or output sizes of common compression algorithms such as LC77 or run-length compressed Burrows-Wheeler transform. During the study of these measures, a remarkable property has been discovered. In a series of papers, it was proved that any two measures in the highlighted set are separated by a polylog n factor for every t. Thus, all these measures are up to polylog factor measuring the same quantity. Let us thus take one of them as a representative. Since LZ77 is the most commonly used lossless compression algorithm, we will use Z as the representative. For a number of other measures, it was shown that there exists a text T on which that measure is larger than Z by a factor of n to epsilon, where epsilon is some constant larger than 0. Although possibly larger than LZ77, these measures, however, often support faster queries. LZ is one of the last compression measures for which we do not know in which group it is. In addition to understanding lossless compression, being able to classify repetitiveness measures in this way has some algorithmic consequences. Namely, it is known that any structure which is always separated from LZ77 by a polylogarithmic factor needs to spend at least log n over log n time to decode any given symbol of the underlying text T. This implies that if we are able to show that LZ is in the first group, we automatically have a lower bound on random access on LZ compressed text. Let us take a closer look at what is known about LZ. LZ is a modification of the LZ77 algorithm, and it was introduced by Kreft and Navarro in 2010. We will give a formal definition shortly. For now, let us review what is known about the size of its output. In 2013, Kreft and Navarro established the following. First, they showed that under a suitable encoding of its output, LZ achieves a compression that can be bounded in terms of the empirical entropy hk of text, for context length k not exceeding log base sigma of n. As we have seen earlier, this does not, however, prove that LZ always compresses close to LZ77. Second, Kreft and Navarro noted that since LZ is a special case of LZ77, it holds that Z is smaller or equal than Z end. The key difficulty is proving the inequality in the other direction, namely that the size of LZ can be bounded in terms of the size of LZ77. Kreft and Navarro conjectured that such inequality holds with a factor of 2. This conjecture is still open. Let us now look at the lower bounds on the size of LZ. In their 2013 paper, Kreft and Navarro also described a family of strings for which the ratio between Z and Z approaches 2. This shows that their conjecture cannot hold with a factor less than 2. Recently, this lower bound has been improved to a family of strings over a binary alphabet. The family of strings given by Kreft and Navarro required alphabet of size linear in n. Let us finally look at queries that can be performed on the LZ compressed text, focusing on one of the most fundamental query, that is random access. In 2010, Kreft and Navarro observed that with the suitable encoding of LZ parsing, we can in O of L time decode any length L substring of text if it is a suffix of a phrase. However, when it comes to decoding arbitrary symbols of text, the best solution prior to this work was achieved via grammars. Since we can build a balanced grammar of size O of Z log n, we can also support random access in O of log n time on a structure of size O of Z end log n. Given the above situation, in our paper we focus on the following problems. First, we ask whether LZ can be bounded in terms of LZ77 up to polylogarithmic factors. This claim is slightly weaker than the conjecture of Kreft and Navarro, but this would nevertheless put LZ in the group of strong dictionary compressors and more importantly, transfer the existing lower bounds. The second question we ask is whether it is possible to support random access queries in polylogarithmic time using only O of the end space. No techniques that would allow achieving such trade-off are currently known. We are now ready to state our results. Our first main result is that z end is O of z times log squared of n. This is the first non-trivial upper bound on the size of LZ end parsing in terms of LC77. In addition to putting LZ end among the strongest repetitiveness measures, as discussed earlier, this transfers the existing lower bounds on random access to LZ end compressed text. In the paper, we generalize this upper bound in few different ways. For example, we show that z end is always bounded by O of delta times log squared of n. Since delta is a measure of repetitiveness that does not change after reversing the string, this implies that the size of LZ end parsing for the string and its reverse differs by at most a factor of log squared of n. We also show how to generalize our upper bound to the case where there exists some limit L on the maximum phrase length. We prove that with such restriction, LZ end compresses the text similarly to what would be achieved with LC77 with the same restriction on the phrase length. This in turn shows that if we aim for value of L that does not affect the parsing size by more than polylog n, it suffices to set L to roughly n over z, that is the average phrase length in LC77. Such value in many cases is a lot smaller than n. In fact, a fast streaming algorithm for this variant of LZ end parsing is known, and our bound explains why it performs well in practice. Our second main result concerns random access to LZ end compressed text. We provide the first solution that achieves polylog n query time and takes O of z end space. This improves the previously smallest structure on LZ end by log factor. Our solution is achieved via new techniques that are potentially of independent interest. We then generalize this data structure to support other queries in the same time and space. More precisely, we show how to compute carpe diem fingerprints for substrings of the text. As a corollary of this result, we obtain a structure that can answer LCE queries in linear space and polylog n time. Due to the use of carpe diem fingerprints, the query works correctly with high probability. In this talk, we will focus on proving the first main result. Let us formally define LC77 and LZ end compression. The LC77 algorithm greedily partitions a given string t left to right, taking at each step the longest block having an earlier occurrence. The blocks included in the parsing are called phrases. Let us look at the example string. Suppose we already partitioned the first 10 characters of the text into phrases. To compute the next phrase, we find the longest prefix of the unprocessed suffix of t that occurs earlier. In this case, the longest such prefix has length 3 and an earlier occurrence at position 6. This earlier occurrence is called a source of a phrase. Thus, the next phrase is a substring of length 3. Each phrase is encoded using a pair of integers containing the phrase length and the position of a source. We then continue in the same way. The longest repeating prefix for the remaining suffix has length 6 and an earlier occurrence at position 4. Whenever a symbol occurs for the first time, we encode it using a pair that stores 0 as the length and the symbol as the position. The example text has 7 phrases and thus z of t is equal to 7. The LZ end parsing is defined similarly to LC77, except we require that there exists a source ending at the phrase boundary. For example, to compute the next phrase in the example text, we observe that although we can find a repeating prefix of length 3, every possible source of that substring ends in the middle of a phrase. The answer in this case is thus a shorter substring, namely of length 2, with a source starting at position 6. For the next phrase, we have a similar situation where, despite a repetition of length 2, there is no occurrence of AA ending at the phrase boundary. We can, however, find an occurrence of a single A. The size of the resulting parsing, and hence the value z end for this text, is 11. For simplicity, the encoding of phrases in the LZ end parsing here is the same as for LC77, but in practice it is often better to replace the starting position of a source with a number of a phrase at which the source ends. Note that although not apparent from this example, not in every case the longest phrase with an earlier occurrence ending at the phrase boundary will be found by first finding the longest repeating substring and then truncating it to the nearest phrase boundary. In general, finding the next phrase in the LZANT parsing may require inspecting also shorter prefixes, since they usually have more occurrences and therefore a higher chance of ending at the phrase boundary. We are now ready to present the proof of the main result of the paper, namely that the size of LZANT parsing is at most O of z times log squared of n. Let Lj denote the length of the jth leftmost phrase in the LZANT parsing. We will call the jth leftmost phrase special if either it is the last phrase in the parsing, or j is between 2 and zn minus 1, and the length Lj is bigger or equal than Lj minus 1 divided by 2. In the example below, green phrases are special and the red phrase is not. Intuitively, a phrase is special if its length is either within some small constant factor from the length of the preceding phrase or longer. In particular, a phrase that is many times longer than its predecessor is also special. Let z-end prime denote the number of special phrases in the parsing. Observe that z-end is bounded by O of z-end prime times log n. To see this, note that if we take any group of consecutive phrases that are not special, their lengths from left to right must decrease by at least a factor of 2 every time. Thus, such block can only contain log n phrases. To show our main claim, it is therefore sufficient to bound the number of special phrases. More precisely, we will show that their number is at most O of z times log n. To show that, let us first denote by Sm the set of all length m substrings of the string t infinity, which is a concatenation of infinite number of copies of t. The main idea of the proof is that with each special phrase, say of length L, we associate exactly L substrings from the set S2 to k, where k is the smallest integer such that 2 to k is greater or equal than 6L. As visualized in the figure, the associated substrings are precisely the L substrings of t infinity of length 2 to k, whose centers are either strictly inside or at the beginning of the phrase. The intuition for choosing 2 to k to be at least 6L is so that all the associated substrings cover the preceding phrase. This will be used later in the proof. Our assignment has the following two properties, which will be proved next. First, all substrings associated with any given special phrase are distinct. Second, each substring is associated with at most 2 special phrases. Observe that these two facts already imply that z-end prime is O of z log n. To see this, note that by the two properties, the total number of times we perform an assignment of some substring of length 2 to k is bounded by twice the size of the set S2 to k. On the other hand, note that we have defined k so that 2 to k is on the order of L, and in particular less than 12L. This means that each time the length 2 to k is used, we perform at least 2 to k divided by 12 assignments. By the above argument, the number of phrases for which a value of k is selected is therefore bounded by 2 times the size of the set S2 to k divided by 2 to k over 12. Recall now the standard upper bound on the size of the set S2 to k, that is z times 2 to k. This bound is a standard result following from the fact that any substring must by definition of LZ parsing have an occurrence overlapping some phrase boundary. Using this upper bound, we obtain that the number of phrases for any value of k is at most 24 times z. It remains to sum the number of phrases for all possible k to obtain that the number of special phrases is O of z log n. We will now prove the missing two lemmas. The first lemma states that all substrings associated with a given phrase are distinct. Suppose that there exists a special phrase for which among the associated substrings there are x and x prime that are the same. Let y be a substring of text containing both x and x prime as substrings. The string x is a border of y, and thus y has a period p equal to the shift of x with respect to x prime. Since x and x prime have their centers inside or at the beginning of a length L phrase, our period must be smaller than L. Let SS denote the longest substring of y centered at the boundary between the two phrases, such that length of S is a multiple of p. We claim that the length of S is greater than L. To see this, let us compute how many full occurrences of a period p fit in y starting from the middle of SS. Looking to the left, we see that the substring y starts no later than the beginning of the rightmost substring assigned to the phrase. The distance to the left boundary of y is therefore at least 2 to the k minus 1 minus l plus 1, which is greater or equal than 2l, since 2 to the k minus 1 is greater or equal than 3l. By the symmetric argument, the distance to the right boundary of y is at least 2 to the k minus 1. It is therefore sufficient to focus on the left side. Since p is smaller than l, we thus obtain that the length of s has to be greater than l. This, however, implies that the string s is a strictly better candidate for the current phrase indicated in red, since it starts at the same position and has an earlier occurrence ending at the phrase boundary. This contradicts the red phrase being included in the parsing. It remains to prove the lemma, stating that each substring is associated with at most 2 special phrases. Suppose that there exists a string x of length 2 to the k that was assigned to at least 3 phrases, and let us take 2 of those phrases that are not adjacent in the parsing. The 2 phrases are marked in green, and the 2 occurrences of x associated with each of them are shown in red. The intuition for why such configuration cannot occur is that after a substring is assigned to a phrase, from now on it has an occurrence in T with the phrase boundary strictly inside its right half. The line in the figure marks the phrase boundary that is now in the right half of some occurrence for every substring associated with the special phrase on the left. Let S2 denote a substring such that the left half of x concatenated with S2 ends at that phrase boundary. Let us also mark where S2 occurs in the other copy of x. Consider now the start of the phrase preceding the special phrase on the right. Let S1 be a suffix of the left half of x such that S1 starts at that boundary. As before, we also mark where S1 occurs in the other copy of x. Observe that since k is chosen so that 2 to the k minus 1 is greater or equal than 3l, and the phrase on the right is special, it follows that S1 is entirely contained in x. However, since the string S2 is non-empty, this implies that the string S defined as the concatenation of S1 and S2 is longer than the phrase defining S1, which is indicated in red. Since, however, S has an earlier occurrence in T ending at the phrase boundary, this yields a better candidate for the red phrase. This concludes the proof of the last missing lemma and thus also of the main result. Many interesting avenues for future work remain. The most immediate problem is to determine the tightness of our upper bound, or prove that LC-end is separated from LC77 by a smaller gap. Another interesting question concerns LZ-end-like parsings, that is, parsings that have the property that each phrase has an earlier occurrence ending at a phrase boundary, but which are not necessarily computed greedily from left to right. It is not known whether finding the smallest such parsing is NP-hard. This in turn raises the question about the approximation ratio and whether the ratio of the greedy approach can be improved. The second group of questions is related to compressed data structures on the LC-end parsing. The first question concerns the construction of our structures. The presented data structures can either be constructed deterministically and support queries in expected time, or in expected polynomial time and support worst-case queries. The deterministic construction with worst-case queries remains open. Another interesting question is about supporting queries other than random access and computation of Karp-Rabin hashes on LZ-end parsing. Finally, it is interesting to explore whether the randomization technique introduced to obtain linear space random access on LZ-end can be used to improve other problems. For example, can it be used to obtain linear space queries on LC77? Thank you for listening to this talk.